which is more stable? More alpha, more stable. More the alpha hydrogen. Now we can also explain by hyperconjugating structure. More the alpha hydrogen. If both orbitals are filled, then there is a no linear combination of atomic orbital. Now what is the meaning of SPTR? And this is a half filled. I am talking about p orbital. Now why isobutene is the most stable isomer of butene? Hi, hello to everyone. Now today we are going to study hyperconjugation in alkene and free radical. Now let us consider the example of alkene. So today's heading will be hyperconjugation in alkene. So means first of all you have to remember that more the alpha hydrogen in alkene, more will be the stability. Just like a carbocation, more the alpha hydrogen in alkene, more will be the stability. Now in order to count alpha hydrogen, this alkene has 12 alpha and this alkene has 6 alpha. So which is more stable? More alpha, more stable. Means 12 is more than 6, that's why first is more stable than second. So write down heading hyperconjugation alkene, and the first statement, more the alpha hydrogen alkene, more will be the stability. Pause the video, write the heading and write this example. Now, how hyperconjugation actually occur in alkene? So let us consider this example of propene. In propene, basically what happens, there is a overlapping between sigma and pi star. There is an anti-bonding pi star of this alkene. Means the overlapping takes place between sigma and pi star. This type of conjugation is known as hyperconjugation in alkene. Means there is a vacant orbital of anti-bonding of pi star and there is a sigma electron. This sigma overlap with this pi star, and this is known as hyperconjugation. If the specifically question asked in exam, the type of hyperconjugation in alkene, then we will write sigma and pi star. In general, hyperconjugation is sigma p conjugation. Got it? So you have to remember the hyperconjugation in alkene is known as sigma pi star conjugation. Got it? Now, second explanation is this alkene has 3 alpha and this alkene has 6 alpha. Now, I will explain you why more alpha, more is the stability. In the first example, in order to draw hyperconjugating structures, what we are doing? We are drawing hyperconjugating structure. So, what we will do? First of all, we will remove the H in form of proton. The proton will be removed. There will be a negative charge. Now, this is a hyperconjugating structure. Similarly, I will remove H2. There will be a negative charge. Again, this is a hyperconjugating structure. Similarly, I will remove S3. There will be a negative charge. Again, conjugation. This is a hyperconjugating structure. This means this alkene has less number of hyperconjugating structure in compared to this. Means more the alpha hydrogen, more we can remove proton, more will be the conjugation. Now, if I mark the hydrogen, there will be a 6 hydrogen. I can mark them as H1, H2, H3, H4, H5, H6. This means more number of hyperconjugating structure, more sigma electron will be delocalized. So that's why more the alpha hydrogen, more will be the stability. Got it? So you have to write second explanation, more the alpha hydrogen, more will be the stability. And the first explanation is more the sigma electron, more will be the conjugation with pi star, more will be the stability. The second explanation is more the alpha hydrogen, more will be the hyperconjugating structure, more is the stability. Now in hyperconjugation in free radical, again in free radical, more the alpha hydrogen, more will be the stability of free radical. More the alpha hydrogen, more will be the stability of free radical. The first one has 9 alpha, second one has 3 alpha, more the alpha hydrogen, more will be the stability of free radical. So first of all, pause the video and write the heading, hyperconjugation in free radical. More alpha hydrogen, more is the stability in free radical. Now, why more alpha is more stability in free radical? Why more alpha, more stable? Because in case of free radical, the hybridization of this carbon is sp2 hybridized. This means it is a half filled orbital and this sigma is a filled orbital. So there is a overlapping between filled and half filled. In case of carbocation, there is a overlapping between filled and vacant orbital between sigma and p. In case of radical, it is overlapping between sigma and half filled orbital. So this means this is again a sigma p conjugation. Means more the alpha hydrogen, more will be the overlapping, more will be the dispersion of this radical. Now in this example, there are 9 alpha H. Means the 9 sigma electron can overlap with this vacant or with a half-filled orbital. This means the electron will be delocalized among 9 CH bond. Got my point? More alpha H, more will be the overlapping, more will be the delocalization of free radical. So that's why more the alpha hydrogen radical, more is the dispersion, more is the delocalization, more will be the stability. Now we can also explain by hyperconjugating structure, more the alpha hydrogen, more is the stability of alkene in free radical. Now in free radical, more alpha, more stability. How can we explain this by hyperconjugation? Just remove H dot, there will be a formation of pi bond. I remove this H1 in the form of H dot, homolytic cleavage, and there is a formation of pi bond. Similarly, I can remove H2 dot, I can remove S3 dot. That's in order to get how many hyperconjugating structure I will get. We will get 9 alpha H. This means we can remove hydrogen 9 times in form of H dot. We can form 9 alkene, means 9 hyperconjugating structure. Means 9 time radical becomes stable because of this complete octet and because of this neutral structure. So that's why more alpha H, more is the stability in free radical, because more number of hyperconjugating structures. Got it? So 9 alpha, 9 hyperconjugating structure, 6 alpha, 6 hyperconjugating structure. So 9 is more stable than 6. Now one more explanation is, I am explaining you why more alpha more stable in free radical. We can explain by also the linear combination of atomic orbitals. So this is a filled orbital, means I am talking about this sigma, and this is a half filled, I am talking about p orbital. So whenever these two orbitals will overlap, two new orbital will form. Now electron will be filled from this low energy level. This represents low, this represents high energy. So initially these two orbitals are there. After overlapping, two new orbital will form and we will start filling electron from lowest energy. Now this is the drop of energy. The energy of 2 electron will drop and energy of 1 electron will increase. So what is the net effect? Net effect stability will increase. So that's why hyperconjugation is less effective in free radical, because of drop of 2 electron and increase of 1 electron, net drop of 1 electron. While in case of carbocation, this orbital is vacant. That's why significantly drop in energy of 2 electrons. So you got my point? Radical is less effective, but still hyperconjugation will operate in free radical because of drop of energy of 2 electrons. So what is the net conclusion? Net conclusion is more alpha H, more stability of free radical, more alpha H, more stability of alkene, more alpha H, more stability of cation. We can also understand one more concept by using that orbital. Hyperconjugation will not operate in carbonyl. In carbonyl, there is no hyperconjugation. Now, why carbonyl hyperconjugation will not operate? Because in case of carbonyl, this is a filled orbital. If both orbitals are filled, then there is a no linear combination of atomic orbital. The drop of energy and increase in energy will be same. That's why no hyperconjugation in carbonyl. You have to remember, hyperconjugation will not operate in carbonyl. This you have to write in your notes. Hyperconjugation does not operate in carbonyl due to fully filled orbital in carbonyl. This means this sigma will not undergo conjugation. Now try this. You have to compare relative stability of following. Pause the video and try all these 4 examples. Which one is more stable? You have to count number of alpha hydrogen as well as you have to mark the alpha carbon. Just circle the functional group and mark the alpha carbon. Now this is the answer. In first example, these are the alpha. This means 10 alpha H and this has 3 alpha H, more stability. In second example, there are 4 alpha hydrogen. In this, there are 7 alpha hydrogen, more alpha H, more stability. In third, 9 alpha H and 1 alpha H. More alpha H, more stability. In fourth, 4 alpha and 8 alpha H. More alpha H, more stability. Now try this. Now, again example fifth, first one has 1 alpha H, second one has 7 alpha H, second is more stable. In sixth, it is a 3 degree, 7 alpha, it has 1 alpha, means 3 degree is more stable than 1 degree. Now, in 7, this is isolated diene. So, in case of 2 alkenes, what we will do? First, we will check resonance. In absence of resonance, we will count alpha of individual alkene. You have to count alpha of individual alkene. The first alkene has 10 alpha and this has 4 alpha. Now in this example, this has 6 alpha and this has 3 alpha. This means first is more stable. Now in 8th, total 12 alpha H and this has 4 alpha H. Again more alpha, more stability because of hyperconjugation. Try these two examples. Now in 9th, second is more stable because of resonance. First we will check resonance. Double bond conjugation with double bond. This is a conjugated dienes and this is an isolated dienes. The first is more stable because of resonance stabilization. Now in 10th, you have to remember, this is cis alkene. Cis means it is on same side. Trans means it is on same side, opposite side. So this means it has 6 alpha H, opposite side trans has 6 alpha H. Number of alpha are same, number of hyperconjugating structure are same, stability of hyperconjugation is same. So that's why we will consider the steric strain. Trans is more stable because of steric strain in cis. Now, what is the meaning of steric strain? Steric strain means strain due to their van der Waals size, because of repulsion of their size. This van der Waals repulsion is known as steric strain. Now, this steric strain is more in cis, less in trans. Why less in trans? Because they are opposite to each other. Since they are opposite, so less steric, less van der Waals. Since they are on same side, more steric, more van der Waals. You got it? Steric strain means repulsion due to their size, means van der Waals radii. So you have to remember trans is more stable than cis alkene. Trans to butene is more stable than cis to butene. So write in your notes, trans is more stable than cis. Now you have to remember some special point. That point will be always dominating. Now, what is the meaning of SPTR? Special point to remember. S means special, P means point, to remember. Now, isobutene, transbutene and cisbutene. What you have to remember? Isobutene is the most stable isomer of butene. Isobutene is the most stable isomer of butene family. Among butene, means one butene, cis, trans and isobutene, which is the most stable? This isobutene is the most stable isomer of butene. Now, trans is more stable than cis. I already explained you because of this van der Waals repulsion. Now, why isobutene is the most stable isomer of butene? We can explain this by a factor of heat of combustion. By data of heat of combustion, we came to know that isobutene is the most stable isomer of butene. Now we want to explain what is the exact reason behind it, why isobutene is most stable. In case of isobutene and trans 2-butene, there are different hyperconjugating structure. First of all, count alpha H, 6 alpha, 6 alpha and 6 alpha. Means number of alpha H are same. So what is the difference? If I draw hyperconjugating structures, this is the hyperconjugating structure of isobutene. Again, this is the hyperconjugating structure of trans 2-butene. Can you see difference between hyperconjugating structures? In case of isobutene, these hyperconjugating structures are of 1 degree carbonyl, and in case of trans 2-butene, hyperconjugating structure are of 2 degree carbonyl. So which is more stable? 1 degree is more stable hyperconjugating structure. 2 degree is our unstable hyperconjugating structure. Got it? Why unstable? Now we can explain with the help of inductive effect because of plus I of this. This means although both have same number of alpha hydrogen, but the hyperconjugating structure stability are different. This has 1 degree, this is 1 degree, 2 degree. This means 1 degree is more stable than 2 degree. If we compare cis and trans, both have same number of alpha, both have same hyperconjugating structure. If I draw hyperconjugating structure of trans 2-butene, 2 degree carbonyl will form. If I draw hyperconjugating structure of cis 2-butene, again 2 degree carbonyl will form. So in this case, all factors are same. That's we go for van der Waals repulsion or steric repulsion. While in case of isobutene, the difference lies in stability of hyperconjugating structures. Got it? So you have to remember, isobutene is the most stable isomer of butene because of stable hyperconjugating structure. Most stable member among the family of butene. Got it? Now that's all for today. Now you have to revise all this and we will do later practice on. If you like the lecture, then please like and subscribe my YouTube channel and spread a word regarding my YouTube channel among your friends and your relatives. Thank you. Jai Hind.